Hello, Science Alliance. Hello, it's Lara here from Theory of Science. It's lesson 10 of forces and motion. We're doing momentum. Right, I have asked you, well, sort of 3 proper questions. If an elephant and a mouse charge towards you at the same speed, which one is going to hurt more? I shouldn't have mentioned an animal with tusks, really. It's not about tusks, it's about something else. I asked you to give a reason for your answer, and question 3 I'll start with. I said, why was my starter question slightly wrong based on previous lessons? I kind of changed my mind about this, right? So the question was, an elephant and a mouse charged towards you at a velocity of 5 meters per second. And I looked at it and I thought, I was almost trying to go wrong so that I could test you. I was like, haha, I'll put in a velocity, but velocity is supposed to have direction, and I haven't put in a direction. You remember this? We've talked about vectors and scalars. So remember, a scalar is something that can be described with just a number and a unit. So like, how long did it take you? 5 minutes. 5, the number, minutes, the unit. Time is a scalar, because that's a perfect description of a time. Velocity is a vector, which means it has to have a number and a unit and a direction. So like 5 meters per second would be a speed. If it's 5 meters per second to the west or to the right, then that's a velocity. And I was like, haha, I have written a speed and not a velocity. And then I realised, I've put towards you, haven't I? A mouse charges towards you at a velocity of 5 meters per second. I think that's fine. So it is correct, in fact. So trick question, sorry. Right. The answer to the first ones, the elephant is going to hurt you more because, apart from the tusks, it's also harder to stop. So what we're looking at today is this idea of sort of unstoppability, which in physics is called momentum. So a little starter question for you then, to start you thinking about momentum relationships. I haven't got a very floppy, this is the problem, isn't it, when you use Lego for everything. I've got a very floppy Lego phone holder at the moment. Let's give it a squeeze. There we go. You're running down a hill, right? What would make it harder for you to stop? Choose as many answers as you like. So this is just to get us thinking about how we kind of naturally feel about momentum. If you were wearing a heavy rucksack, would that make it harder for you to stop if you were running down a hill? If the weather was warm, would that make it harder to stop? If you were running really fast, would it be harder to stop? If you were running in slow motion, would it be harder to stop? It might be 1 answer, it might be 4 answers. What do you think of that list would make it harder for you to stop? There's 5 seconds. 4, 3, 2, 1. The correct answers are, if you were wearing a heavy rucksack, it would be harder to stop. And also, if you were running really fast, it would also be harder to stop. So let's put our ideas about momentum into an equation. Here we go. Look at it. Isn't it lovely? Momentum is exactly equal to a thing's mass times its velocity. So if you've been before, which I'm hoping you have been to some of these previous force and motion lessons, here are some questions for you. What are the units of momentum? Oh, and what is this kind of relationship called? What are the units of momentum? So momentum equals mass times velocity. So you would probably immediately know that, like, if mass was 2 and velocity was 3, then momentum would equal 2 times 3, which is 5. But remember, whatever you do to the numbers, you do to the units as well. So what are the units of mass? What do we measure mass in? What are the units of velocity? And if you times them together, what do you get? It's not like a trick question. Just times the units together. And those are the units of momentum. And what is this kind of relationship called? Like, we've just done Hooke's law, haven't we? What's it called if you just have a thing is a thing times a thing? If you're wondering what I'm doing, I'm taking this opportunity to test my pens, because the situation is dire. Oh, that's a good one. Oh, yeah. Have you got it? I was getting some great answers on Facebook the other day, and none of them were right, really, but people were really thinking. I was getting a lot of newtons per second squared, meters per, kilograms per something. Let's have a look. The units of momentum are, well, the unit of mass is the kilogram, okay, like the standard unit. Obviously, you could say gram or whatever, or milligram, but the standard unit is the kilogram. The standard unit of velocity of meters per second. Don't get distracted by direction. That's not the unit. The unit of velocity is meters per second. So just times them together, and what do you get? Kilogram meters per second. It's a bit weird, isn't it? Kilogram meters per second is the unit of momentum. You'd think they'd have like called it a fun name like the Joule or the Newton, but no. So it's worth, this is more kind of A-level, but I think it's just such a useful thing to know at iGCSE. So you know how like velocity or speed is measured in meters per second, right? But this line here, this dash where you say per, it's also telling us the equation, because the units of speed are meters per second, how many meters you go per second. But the equation for speed is meters divided by seconds, all right? So if you've got to remember a lot of equations now for iGCSE, but actually if you know your units, you don't have to remember it. The answer is there. So speed is meters per second, and it's meters distance divided by seconds time. So momentum is mass, kilograms, times velocity, which is meters per second. Be careful, you want to say like kilograms per meters per second, but the equation isn't dividing, the equation is times. So you just don't put anything there. Kilogram meters per second, we'll be saying it a lot. And what's that relationship called? It is a directly proportional relationship. How lovely. Which kind of makes sense, right? When one goes up, the other goes up by the same amount. Like if you put a backpack on that was exactly equal to your mass, then you would end up running down a hill twice as fast. So that kind of makes sense, right? If you ran down a hill, if you ran twice as fast, you would be twice as hard to stop. If you had a backpack on that weighed twice as much, you would be twice as hard to stop. Yeah, it kind of makes sense. Let's see if you've understood. Here we go. Which is harder to stop? Yeah, I looked up actual animals that weighed this amount. Which is harder to stop? A 10 kilogram honey badger rolling down a hill at 1 meter per second, or a 1 kilogram moon rat, yeah, it's a thing, rolling at 10 meters per second. So you've got a honey badger with a mass of 10 kilograms, but its velocity is 1 meter per second. You've got a 1 kilogram moon rat rolling at 10 meters per second. Which one of those is harder to stop? Couple of people on Facebook the other day talking about like, oh, well, one hill is steeper than the other. No, don't worry about the hills. Just look at the question. Just look at the information that you've been given. Don't try and be too clever about it. I think you're getting this. Some people were saying the badger the other day, but that's not right. The answer is, well, let's have a look. So their momentum, so how hard they are to stop, we'll call that their momentum, is their mass times the velocity. So the mass of the badger is 10 kilograms, but its velocity is 1 meter per second. So 10 times 1 is 1, right? So it's got a momentum of 1 kilogram meter per second. The moon rat, which by the way isn't a rat, biology, just sort yourselves out. It's 1 kilogram mass times 10 meters per second velocity, which is, it's also got a momentum of 10. So the answer is they're both equally difficult to stop. Well done if you got that. Here are your symbols, if you don't want to have to write out the whole equation. We know that the symbol for mass is a little m. We know that the symbol for velocity is a little v. So the symbol for momentum is obviously a small p. So if you want to write this equation out quickly, it's little p equals mv. I apologise on behalf of science. What can we do? So here are your questions. I'm actually really proud of these questions. The ones in green, now if you're watching on YouTube, especially if you're watching on catch-up, please just try them all. If you're watching live and you want to keep up with me, the ones in green you should definitely do. They're pretty standard. The ones in orange I've tried to catch you out. And the extra challenge, again, super proud of myself. This is really going to exercise your brains, I think. Got some real teacher smugness. So the ones that I want you to do that are hopefully fairly straightforward. Momentum equals mass times velocity. A car with a mass of 1,000 kilograms travels at a constant 30 meters per second. What is its momentum? A cat running at 3 meters per second has momentum of 6 kilogram meters per second. What is its mass? Those are the straightforward ones. If you've got time, have a go at these. What's the momentum of a car with a mass of 2,000 kilograms travelling at 5 kilometers per second? and a ball weighing 20 newtons falls at 5 meters per second. What is its momentum? And then, yeah, I'm very proud of this. Why is it mass and not weight? Can't you say momentum equals weight times velocity? Like, aren't mass and weight a sort of similar thing? Can you explain to me why that can't be weight, it has to be mass? How are you getting on? I'll give you 30 more seconds. So your clue for the extra challenge is, can you think of a situation where something could weigh very little but have a lot of momentum? If you've totally finished and you're really bored, don't forget you can like and subscribe. You can go over to my Facebook page where there's a post and tell me how you're feeling about this. Right, 20 seconds, then we'll go through it. All right, here we go. I'll flip you around and talk you through the first two. The sort of hopefully fairly straightforward ones. So the first one, here we go. We've got momentum equals mass times velocity, and you just plug the numbers in, right? So the car's mass is 1,000 kilograms, and it's times 30 meters per second, which equals, well, 30 times 1,000 is 30,000 kilogram meters per second. Well done if you got that. The second one, you've got to do a little bit of rearranging, haven't you? Do you remember how we did this? So I'll just do it in small, let's do it in a different colour. I'll do it in the handy little code. If little p equals mv, right, that's momentum equals mass times velocity. If you want to get mass on its own, because we're looking for the mass, then you divide, we need to get rid of this v. So if you divide that side by v, then the v's cancel out, just like 5 divided by 5 is 1. But whatever you do to this side, you've got to do to that side. So you divide momentum by v as well. So mass is equal to momentum divided by velocity, which is 6 kilogram meters per second divided by 3 meters per second, which is 2. Now, this is where, I cannot emphasize this enough, it's really, really, really good idea to write your units in, even if you're in an exam. You might think, oh, that's going to take too long, like time's ticking, I'll just write 6 divided by 3 equals 2. But no, this is a great way of checking, because look, can you see that I've got 6 kilogram meters per second divided by 3 meters per second. So just like numbers do, the units cancel out. So I know straight away that my answer is going to be in kilograms, and I'm looking for a mass. So it's a really good way of knowing, okay, I've arranged my equation correctly. There we go. So the answer is 2 kilograms. Well done if you got that. Right, let's do these other ones then. I was ever so smug about. What's the momentum of a car with a mass of 2,000 kilograms travelling at 5 kilometres per second? Did you see that I was trying to catch you out here? There are actually 2 ways that you could have done this one. Stick that down a bit. So if you didn't notice my mean, cunning trick, because velocity is in kilometres per second, right? Not meters per second, kilometres per second. So we've got, let's just do it in code. Little p equals mv. So our mass is 2,000 kilograms. If you didn't notice this and you just wrote 5 kilometres per second and times those 2 numbers together, that would actually be fine as long as, so what's 2,000 times 5 is 10,000, yeah? That you would get a mark for that, and you would get another mark for units as long as you wrote down the correct units. So again, if you've written your units in your working and you just put those units together, you could write kilogram, kilometres per second, and that would be okay. That would get you marks at iGCSE. That's not wrong. The unit of momentum can be kilogram, kilometres per second, just like a unit of length could be like centimetres or millimetres. It's not a great idea because later on, quite often, they'll get you to use a number you've worked out before to do a different calculation. So if you were starting to do a different calculation, you'd probably want that to be in metres. So if that was a question on its own, you'd get a mark. But a better thing to do would be to convert the kilometres into metres. Remember, we did this in maths. So 5 kilometres, if you're travelling 5 kilometres per second, there's 1,000 metres in a kilometre. So 5 kilometres per second is the same as 5,000 metres per second. So 2,000 times 5,000, that's a lot of noughts, isn't it? What's that? 10 million. And that would be kilogram meters per second. So well done if you did either of those things. That is good. Right, this next one. What brilliant revision. I love it when all the stuff you learn comes together. A ball weighs 20 newtons. It falls at 5 meters per second. What is its momentum? Well, hang on. Momentum uses mass, doesn't it? We're going to have to change this weight, 20 newtons, into a mass. How do we do that? Do you remember the equation? I'm just loving my new coloured pen, so I'm using them all. Do you remember that weight equals mass times little g? Yeah? So little g is the strength of Earth's gravitational field. You remember? So anything with mass gets like pulled on by Earth's gravitational field. And Earth's gravitational field happens to be 10. The units are 10 newtons per kilogram. So every kilogram of stuff on Earth gets pulled on with a force of 10 newtons. 10 newtons per kilogram. So we've got a weight. We know what little g is, hopefully. We know that it's about 10, 9.8 actually, if you're doing iGCSE, but most of the time they'll let you use 10. So we can use that to find the mass, can't we? Again, let's rearrange. So the mass equals weight divided by little g, which in this case is 20 newtons divided by 10 newtons per kilogram. And so the mass is going to be 2 kilograms. The tricky bit in an exam is remembering that that's not actually the final answer. So now we need the momentum. But that's quite easy, isn't it? Little p equals mass times velocity. And we've got our mass now. It's 2 kilograms. And we've got our velocity. It's 5 meters per second. So the answer is And I can see that my units are right because I'm times in kilograms by meters per second. 10 kilogram meters per second. Whew. Is that right? Mass divided by 2 times 10. Yeah, great. Well done if you got all that. Oh, so why is it mass but not weight? Oh, well, again, this is great revision for Newton's laws and things. Imagine being out in space where there is hardly any, let's say basically no gravity. There's no planets or stars nearby to be pulling on you. You've still got a mass, haven't you? And if someone, I don't know how this is happening, but if someone pushed you and you travelled along, you would still be difficult to stop. You would still have momentum. An elephant in this situation coming towards you in space, remember, there's no forces acting on it. So if you push an elephant in space, it just keeps on going at a constant speed, yeah? If that elephant hit you, it would still hurt. It would still be hard to stop. So it's got mass. It hasn't got any weight because there's no force pulling on it, but it's still got momentum. So that's why it's mass and not momentum. Well done if you were thinking about that. Right, let's have a little break and I'll show you a classic momentum activity you can do with a football and a tennis ball. I didn't want to assume that you guys had footballs and tennis balls, so I didn't say to bring these with you, but if you have got them, you can do this after the lesson, right? This is the classic. What you do is you get a tennis ball and you get a football and you notice how high they bounce individually. So if I just put my ball up to the top of the screen, that's how high the ball bounces. Well, it's about halfway up, isn't it? Notice how high the football bounces. A bit less. So both these things have got momentum, right? They've both got a mass. And they are obviously both travelling at a velocity, a speed. So they're travelling about the same speed, right? About the same velocity, but the football's mass is higher than the tennis ball's. So if they're travelling at the same speed, but the football's mass is higher, which one has more momentum? Same speed, this mass is bigger, so the football has more momentum, yeah? What's going to happen if I put the tennis ball on top of the football and drop them both together? So this is how high it bounced on its own. Let's do it. Let's come back a bit. You ready? Hey! Ah! Oh no. Oh, right under the... Oh, come on, that did not... That's good, isn't it? Let's do it again, but I won't bother to rescue it this time. Why does that happen? Oh, come on. No, I'm going to do it one more time. Ah! Nearly smashed my phone. What is happening is that momentum is always conserved, right? Momentum before a situation is always equal to the momentum after a situation. What's happening is that the football is passing on its momentum to the tennis ball. But because the tennis ball has less mass, it's going a lot faster. Does that make sense? So when the football sort of, passes its momentum onto the tennis ball, the tennis ball gets the same amount of momentum, but its mass is smaller, so its velocity has to be bigger. Does that make sense? We're going to go into it now. But yes, when two things collide, the momentum beforehand is always the same as the momentum after. I put it on a slide in a proper physics way. I'll show you. Proper physics wording. There's no need for me to be crouched on my kitchen floor, making it up as I go along. Here we are. Don't be freaked out. I will explain this in proper normal language. Momentum is always conserved. This is an incredibly important law in physics. If two objects collide, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. If that's not enough words for you, really we should say this is true in an isolated system. So no external forces like friction. I'll tell you what I mean. So for example, if you've got two snooker balls on a snooker table and one snooker ball rolls towards the other snooker ball and collides into it, the momentum of them both before they smash into each other is the same as the momentum after they smash into each other, but you can't think about the external forces. Like, that's not including like air resistance of the air particles pushing into the ball as it rolls, or not including like the friction on the surface of the snooker table, things like that. So if you're just thinking about the things that collide, then momentum is conserved, all right? I'll give you a question. It's not, you can if you like, if you're feeling confident, you could pause the video and answer it. Really, this question is just to get you thinking, and I'm going to tell you as an example to help you understand what I'm talking about. So here we go. This is the sort of thing you see at GCSE. A child riding a bike at 3 meters per second sees a 1 kilogram bag of apples and decides to grab them because, I don't know, it's the Victorian times. So the bike and the child together weigh 20 kilograms, okay? The apples weigh 1 kilogram. Child and bike together weigh 20 kilograms. The bike and the child are travelling at 3 meters per second. What is their new velocity after stealing the apples? I will go through it with you. Take 10 seconds if you like. Do some scribbling down, or just think about it in your head. Get your brain cells whirring. How are you going to go about solving that? Remember, the momentum before is the same as the momentum after. I'm not expecting you to get it, by the way. I'm just giving you a second to take it in and think about it before I go through the answer with you. And then I'll give you one that you can answer yourself. Okay, let's go through it. So, a child riding a bike at 3 meters per second sees a bag of 1 kilogram apples and decides to grab them. So the conservation of momentum law says that the momentum beforehand of the child and the bike and the apples, all the things in this system that we're talking about, that momentum is the same as the momentum afterwards. So let's work out that momentum first, okay? So we want, I'll put momentum before equals momentum after, because that's important. Momentum before equals momentum after. So what's the momentum? Well, the momentum of the child is fairly easy, isn't it? Hopefully. The momentum before is equal to the child and the bike's momentum plus the momentum of the apples. I'm just going to write a little p instead of writing momentum out every time. Plus the apples' momentum. So the child's momentum is just 20 kilograms times 3 meters per second. 20 kilograms times 3 meters per second. And the apples, well, handily in this, it's going to be 0, isn't it? The apples have got 0 momentum because they're not moving. So you would do their mass, which is 1 kilogram times 0 meters per second. I probably would bother to write that down if I was in an exam so that the examiner knows what I'm talking about. So all the momentums added together are 60 kilogram meters per second plus nothing. So it's 60 kilogram meters per second is the momentum of this situation here, okay? Let's write that up there. 60 kilogram meters per second. Can you see how suddenly we've kind of got the information that we need to answer the question? So what we want is this new velocity of the child running off with the apples. So we know that momentum equals mass times velocity. We're looking for velocity, so we times that whole side by mass. Divide the whole side by mass, so the masses cancel out, and we divide that side by mass as well. So we know that velocity equals momentum divided by mass. And look, we've got the momentum because the momentum before is the momentum after, because momentum is always conserved. So this new velocity, we can use the momentum that we've just worked out, 60 kilogram meters per second. And what's the mass? Well, be careful. We've got a new mass, haven't we? It's the child plus the apples. So the child, it was 20 kilograms for the child on the bike, but we've got to add on the apples. So we're dividing that momentum by 21 kilograms, which is our new mass. Whew, what's the answer? Are you ahead of me? Have you already done it on the calculator? 60 divided by 21 equals 2.85714. Well, we'll talk about significant figures later, but for this I'm going to round it up to 2.9. And what are my units? Again, it's so easy, isn't it, to know that I'm on the right track, to know that I've rearranged this equation correctly. Because again, look, see, the kilograms are cancelling out. So my units are meters per second. Is that correct? Is that what I was looking for? Yes, it is. Brilliant. So in an exam, I would be very happy to move on there. Right, is that okay? Try one. And then don't forget, as usual, I'll set you some homework and I'll give you more of these questions that I found on the internet to go through yourselves. But try one and then we'll go through it. Here we go. So this is information you need. Momentum equals mass times velocity. And momentum before equals momentum after. So this time, a car of mass 500 kilograms, it's a little car, travelling at 10 meters per second, hits a stationary car, stationary means staying still, yeah, of mass 2,000 kilograms. They stick together, but they keep moving. What is their velocity after the collision? So it's what I did on the board, but doing it yourselves. And if you have absolutely no idea at all, then that's not a bad thing. I usually take a lot of practice questions to get the hang of these, but if you haven't got a clue, I can't emphasise enough. It'll be fantastic brain exercise, and it'll really help you later if you just practice going wrong. Just write down the equation, stick the numbers in, just do anything. Just have a little crisis on the page, and then you'll really learn from that. Neurons will fuse together. I'm going to do it with you, and then we'll go through it. If you didn't hear me saying at the beginning, do use a calculator. It's not cheating, it's just an essential tool, like trying to build a cabinet without using a hammer. We've invented the calculator, we might as well make the most of it. How are you getting on? Should we go through it? Excuse me. I'll go through what I did. I'll run you through what I did, don't worry if you haven't finished. And then, like I say, I'll go off and find some interesting past paper questions and exercises for you to do to hopefully help you cement it in your brain. But here's what I did, right? So, little car, 500 kilograms, big car, 2,000 kilograms, little car's traveling at 10 meters per second, and then they stick together and we need their new velocity. Well, drawing a diagram usually helps. So first of all, I want to work out the momentum before. So I write down everything I know. I've got the mass of both cars and the velocities of both cars, so this is going to be okay. So the momentum before is the momentum of the little car plus the momentum of the big car, okay? We need to work out the momentum of this whole situation. So the momentum of the little car is 500 kilograms times 10 meters per second. And then we add on the momentum of the big car, which is 2,000 kilograms times nothing, because it's stationary, it's not moving. So the momentum before, I get to be 5,000 kilogram meters per second. Okay, good. Now we want the velocity, right? Here's the situation afterwards. We need the new velocity of this weird combination of cars. We've got the momentum because we know that the momentum before equals the momentum after, and we just worked out the momentum before. So the momentum is 5,000 kilogram meters per second. The new mass is going to be just the masses added together, so 2,500 kilograms. And then, well, we can almost just plug it in, can't we? I would always write your equation at the top so that you can see that you've rearranged it properly. So we're looking for the velocity, so we need to move the mass over there. So velocity is momentum divided by mass, right? New velocity is momentum divided by mass. We know the momentum because it's the same as before. We know the mass, so you just divide them. And what's the only thing I need to do? Yeah, add my units. And if this was a really complicated question at A level, the way that I'd be confident is I'd be like, oh, look, I must have done all this rearranging properly because my kilograms are cancelling out. So I've got an answer of 2 meters per second, and I was looking for a velocity. Huzzah! I'll move on to the next question. Phew. Right, you lot. That is the end of the lesson, except to say next week we'll do a lot more on this, but I just thought to give you like a little inkling. I've got a really, it's like a rubbish sentence and I don't want you to complete it with a rude word. What do you reckon? Momentum is a, I've mentioned this word in the lesson. I've already mentioned this word in the lesson. So just in case you were wondering, how might you end this sentence in a polite physics way? Momentum is a lot of people on Facebook were saying force. No, momentum is not a force, but I'm happy if you said that because next week we're going to look at how momentum and force and time are very intricately linked in a way that Isaac Newton noticed. Momentum is the answer is vector. Momentum is a vector, yes. So that's why when I did this weird moon rat question, I drew arrows, see? And the arrows are the same length because the momentum is the same, yeah? Different directions, but same amount, same magnitude. Right, okay. So that is the end of the lesson. I'm going to go over to Facebook now and see if anyone's left me any answers. Suffice to say that I could not do this job without people supporting me. So thank you so much if you have gone to my YouTube About section and clicked the link and gone over to my website called Coffee. It's good value. I'm so happy with this business model. Enough people, I would be happy with more, but enough people are supporting me with £5 or £6 a month that I can do an iGCSE physics lesson live like this every week except York school holiday time. And I can do a show with like a Lego story time teaching about stuff, and I can do like an all ages home ed lesson. And I can even make a magazine and send it to you to say thank you so much for supporting me, because I know that you don't have to. It's really important to me that everything I do is completely free and accessible to everyone. But it wouldn't work if people didn't pay me for my job. So if you would like a copy of Theatre of Science magazine, which has, this time it's on time, so it's got an article about Einstein's theory of special relativity. It's got a sundial craft that you can make. It's got a beautiful comic about a family that sold time, because my husband is a very good illustrator. It's got an article about a slow worm. It's got some news articles. Very proud of Theatre of Science magazine. I'll send you some diffraction glasses as well, which might help with later iGCSE lessons. Anyway, yes, thank you very much for supporting me. The link is in my About section. Children obviously not talking to you at this point. You can gently nag your parents. Right, that is the end of the lesson, except if you've left me a comment on Facebook, I'm going to come over and see. You may be too busy jabbing numbers into your calculator to leave me any comments. Oh, I've had a comment. Is it going to be from... It is Chloe. I was going to say Chloe, and then I didn't want to upset anyone who wasn't Chloe. Hello, Chloe. Thank you for leaving me a comment. All right, I'm going to go because I'm on Facebook at 11 o'clock actually, in 12 minutes, doing my all ages home ed lesson on viruses. Oh yeah, we've got to make a model of a virus. I've got to get my Play-Doh out. Thank you so much for coming, you lot. Thank you for all your support. I'll see you very soon. Bye.